A black body is an idealized model of matter that absorbs all radiation that falls on the body. So for example, if the black body is subjected to a beam of light, which contains the light waves, then this body will absorb all this electromagnetic radiation. And therefore the electrons in this body start to oscillate back and forth. And recall from our Maxwell-Boltzmann distribution, the temperature of the body is proportional to the kinetic energy of the particles. So therefore the oscillation of these particles occurs because the electrons gain kinetic energy, and therefore the temperature of this body increases, but the temperature does not increase indefinitely. So therefore the electromagnetic radiation that was absorbed by the body that caused these charges to oscillate results in an oscillating electric field. And recall that an oscillating electric field is accompanied by an oscillating magnetic field, which is basically a light wave. So therefore the black body is a perfect emitter of electromagnetic radiation. So it emits the electromagnetic radiation that it absorbs, which is in line with our observation where the temperature stops increasing at some point and thermal equilibrium is established. So a black body is a perfect absorber and emitter of radiation. So note that it does not transmit the incident electromagnetic radiation and it does not reflect it. So we say the perfect black body has an emissivity of 1. And at the other end, if you have electromagnetic radiation that's incident on a white body, then none of that gets absorbed and all of it gets reflected. So therefore the emissivity of a white body is 0. And for a grey body, incident electromagnetic radiation is partly absorbed, so it causes these electrons to oscillate, partly reflected, and partly transmitted. And therefore the absorbed electromagnetic radiation in a grey body causes an oscillating electric field, which causes light waves to be emitted from the body. So note that transmission and emission is not the same. So in reality, nothing is a perfect black body, but a black body can be created using chemical processes. So for example, an ultra black nickel phosphorus alloy, which is used as a coating film, is almost a black body. So we take the emissivity to be around 1. So it's a perfect absorber and emitter of electromagnetic radiation. And on the other end, a shiny mirror is an example of a white body. So it only reflects the incident electromagnetic radiation. It does not absorb or transmit it. And in the middle somewhere you have a combination of both for the grey body. So an example is a human being which has an emissivity of 0.97. So note that some of the electromagnetic radiation that's absorbed is going to be emitted for a human body to maintain its temperature and not increase indefinitely. So note that other chemical processes can cause the emission of electromagnetic radiation. So a typical example is the sun or a star that has internal nuclear reactions that raise its temperature, and that in turn causes chaotic motion of the particles, and the electrons, being the lightest, oscillate back and forth the most, and an oscillating electric field produces electromagnetic radiation. So that's how the sun is able to heat the earth at such a long distance, using electromagnetic radiation. As we saw, the black body is a perfect absorber of electromagnetic radiation, and that causes the oscillations of charges in a black body, which cause oscillating electromagnetic fields, and therefore the black body emits the electromagnetic radiation that it absorbs. Now a black body emits a continuous spectrum that depends only on the body's temperature. So this is the black body spectrum for the different temperatures given here, when the body is heated, from 3000 Kelvin to 6000 Kelvin. So we model the radiation emitted by a black body by plotting the intensity per unit wavelength, so that's in watts per square meter using SI units, and here we've taken our wavelength in nanometers, so we can plot the intensity per wavelength, which is in nanometers. So this is the power intensity of emitted radiation per unit wavelength. And the distribution of intensity of a blackbody spectrum as a function of temperature cannot be modeled using only classical physics concepts. And a blackbody spectrum is described by Planck's blackbody radiation law, which assumes the energy of light is quantized. So without going into the quantum mechanics, this is Planck's blackbody radiation law, which takes the intensity per unit wavelength is a function of the wavelength and temperature. And that's equal to 2 pi by Planck's constant by the square of the speed of light over the wavelength of light to the power of 5, and that's multiplied by the reciprocal of e to the power of Planck's constant by the speed of light on the wavelength of light by Boltzmann's constant by the temperature of the black body, minus 1. So in classical physics, you have the Rayleigh-Jeans equation, which is this first part of Planck's blackbody radiation law. So that predicts that the intensity of light will increase indefinitely with a decreasing wavelength. But this creates the UV or ultraviolet catastrophe, because as we know, when we heat up a piece of metal, for example, like a frying pan, we don't get exposed to X-rays or gamma rays, which are quite deadly. So given that Planck's law assumes the energy of light is quantized, so the black body absorbs and emits discrete packets of energy. So Planck's law has this second term, which results in a decreasing intensity for the smaller wavelengths, which is in line with our observations in reality. Now in reality, this blackbody spectrum is not continuous, it's actually discrete. So experimentally, you'll get discrete points of intensity versus wavelength, and Planck's blackbody radiation law fits well through these points. Now a typical example is the Sun, which has a temperature of 5772 Kelvin. So if you heat a black body to this temperature, you'll get a curve similar to the blue one over here. So as we can see, the peak of this curve occurs in the visible light spectrum. So these are the wavelengths of visible light from 390 nanometers to around 770 nanometers. So therefore sunlight emits all the colors of the rainbow, so the sun is actually white. But we see the sun as mostly yellow because of atmospheric scattering. So some of the wavelengths of light get scattered by the atmosphere. And here we can see a small portion of light emitted by the sun is in the ultraviolet region of the electromagnetic spectrum. So that's this part over here. which is quite small compared to the wavelengths of visible light emitted by the sun. So effectively, if we heat this body, it keeps changing color, and when it reaches the color of the sun, we can determine the temperature of the sun without actually making a physical measurement. Now on the other hand, the human body has a temperature of around 310 Kelvin or 37 degrees Celsius, so most of the light emitted by a human is in the infrared region of the electromagnetic spectrum. And you can see this light using an infrared camera. The peak wavelength that's emitted by a black body, as we can see, decreases with an increasing temperature. So as you can imagine, the hotter the black body is, the higher the amount of radiation that's emitted per unit wavelength. So we have the power intensity per unit wavelength, which in this case our wavelength is in nanometers. So the amount of radiation per unit wavelength is in watts per square meter per wavelength in nanometers. So recall that this blackbody spectrum was determined using Planck's blackbody radiation law, in which the power intensity of emitted light was a function of the wavelength and temperature. So if you've taken calculus, you can determine the peak wavelength, which is where the slope of the tangent to each of these curves is 0, by differentiating Planck's law and setting the derivative to 0. So if you do that, you'll come up with Wien's law, which gives the maximum wavelength of light, which is a wavelength at which the black body emits the greatest amount of radiation per unit wavelength. So this will be equal to a constant on the temperature. And this constant is equal to 2.898 by 10 to the minus 3 meter Kelvin. Now the rate at which energy is emitted, or power, by a black body is described by the Stefan-Boltzmann law. So that's equal to the emissivity of the body by the area by the Stefan-Boltzmann constant by the temperature raised to the fourth power. So the power is proportional to the surface area of the body and to the temperature of the body raised to the fourth power. So for a black body, the emissivity is 1. So for example, the ultra-black nickel phosphorus alloy coating film that we mentioned previously, a star, and so on. And the Stefan-Boltzmann constant is 5.67 by 10 to the minus 8 watts per square meter per Kelvin to the power of 4. So A is the surface area of the emitter, and T is the absolute temperature in Kelvin. So note that the Stefan-Boltzmann law is obtained by integrating Planck's law, which gives the area under the curve of the blackbody spectrum. So I'll leave the derivations to you as an exercise if you've taken calculus. So the Stefan-Boltzmann law allows us to estimate how much energy a star is radiating by remotely measuring its temperature. So for example, heating a black body, which gives a specific color, allows us to identify the star that we're dealing with. Based on the temperature that was required to heat this body and obtain that color. And Wien's law gives the maximum wavelength, so that also helps us to identify which wavelengths are dominant in the blackbody spectrum at different temperatures. Determine the rate at which energy is emitted from a spherical blackbody with a radius of 5 centimeters at a temperature of 1000 degrees Celsius. And also find the peak wavelength of light emitted at this temperature. And we're given a constant in Wien's law, which is the maximum wavelength is equal to B on the temperature. And the Stefan-Boltzmann constant is in Stefan-Boltzmann's law, which gives the power or rate at which energy is emitted from a black body being equal to the surface area by Stefan-Boltzmann's constant by the temperature raised to the power of 4. So therefore the power is equal to the surface area of the spherical body, which is 4 pi by the radius squared, and we'll convert this to meters. So 5 centimeters is 0.05 meters, and let's multiply by 5.67 by 10 to the minus 8 watts per square meter per Kelvin to the power of 4, and let's multiply by the temperature in Kelvin, which is 1000 plus 273 or 1273 Kelvin raised to the power of 4, which gives 4677.8 watts. And the maximum wavelength of light that's emitted is equal to 2.898 by 10 to the minus 3 meter Kelvin divided by the temperature in Kelvin, which is 1273. So that gives a wavelength of 2.28 by 10 to the minus 6 meters. And if you multiply this by 10 to the 6, you get 2.28 micrometers. So this is in the infrared region of the electromagnetic spectrum.